Welcome to our Hanukkah webinar. And I would like to introduce to you Professor Lioz Etgar. Our webinar will be the title of the Who Needs a Miracle When You Have Solar Energy? Professor Edgar is an associated professor in the Institute of Chemistry at the Hebrew University, and his research focuses on the development of innovative solar cells. And he was the first to use, sorry if the name, if I don't pronounce it right, Perovskite, a much simpler cell structure. Professor Edgar was awarded the prestigious Kaye Innovation Awards in 2021 and the Krill Prize in 2016. He has published over 100 articles, hold 8 patents, and he is the founder of Solra, a new startup under the auspices of Yissum. So, Professor, the floor is yours. You can begin, and while I will see Yossi connecting, I will stop and light the candle. Let's see. Thank you.
Okay, thank you very much, Mara. So I will show you today some of, let me share the screen. Some knowledge, or let's say some input about the solar energy in general, and also some development or recent developments that we have in our research lab, trying really to put you in perspective where are we standing and what are the opportunities. And so Mara introduced me already, and you see the title. The idea is to give you really an overview on this field, and also some specific points. If you have any questions, I will be happy to answer, of course. Okay, so let's start. So like 2 weeks ago, probably all of you know, so we had a climate change conference in Glasgow, which all the important and heavy problems were discussed there, of where are we going in this world in terms of pollution, in all this climate change that's happening to us in recent years. And we need to see how we can really solve this. I cannot say that there was really a real conclusions in this conference, but it really opened the mind of a lot of people how to continue. So we have to understand that we live in a greenhouse. What does it mean? It means that finally we have the sun, which reaching the airs and heating our airs. And once it hits the airs, it radiates back. And if we have a pollution of gases, which called greenhouse gases, they absorb this radiate which come from the airs, and these finally heat our atmosphere, which means that the temperature is increasing and increasing. And finally, once we will have more and more greenhouse gases, we will have more and more increase in temperature of airs and more changes in our weather. So this is something that we are already live inside this stuff. And what does it mean? It influences our whole life. It influences our sea level. It affects our weather, as I said. It also affects our underwater life. It causes tsunamis. So those greenhouses gas are not something that we want, and we need to avoid it by using some clean energy. And one of the solutions, let's say, to avoid this is to use solar. And what does it mean, solar? Let's say why to use solar energy, why it's so attractive. You can say, okay, I can use other energy sources. First, I don't know if you know, but we have more solar energy is really absorbed by airs in 1 minute that what we can produce in 1 year by all the fuels that we have, which means this is a really huge source of energy that we are not really taking advantage of it at all at the moment. Of course, it makes us our energy pollution-free, no waste, no emission, no greenhouses gases. And finally, we have sun everywhere, which means that we can take it from one location to another very easily. And we don't need to take care of this point. Maybe we need to take care of the storage, but this is another issue. So what is a solar cell in general? A solar cell is something that we generate electricity from the sun. This is technically what we want to do. We convert it directly from the sun to electricity, no other converter in the middle. First, they were used in satellite and spaceships. But today we are trying, this is what I will show in this lecture, we are trying to push it more and more that will be available. And the mechanism, the main mechanism, and I told you I need to get into a little bit chemistry and physics, but not too much. But the main mechanism is that we need to separate the electron and the holes in the material, which means that we need to separate the negative and positive charges that we have in the material once it absorbs light. And this is the idea. If our material absorbs light and it generates negative and positive charges, which are electron and holes, and they will be separated, then we can generate electricity quite easily. So the solar energy are actually divided to 3 generations. We have the first generation. This is the high quality solar cells, which were first used in space ships and satellites. So they are very efficient, but finally they're expensive to make them, expensive to sell them. And if they're expensive, they will not replace our coal or other source of energy that we have today. And therefore, like 20 years ago, people tried to develop what is called second generation. And the idea was to reduce the cost by keeping the high efficiency of the cell. Unfortunately, the idea is nice, but they still use a very expensive technique to make the solar cells. And the mechanism is still more or less the same. And this why actually the second generation didn't succeed. And more recently, we moved to what we are calling a third generation. This is really a revolution because here we are moving to new materials. We move into to a different mechanism of the solar cell. And finally, this allows us to reduce the cost dramatically while keeping the same power conversion efficiency or the same efficiency of the cell. This also opens a lot of applications, as you can see later. And this is where are we standing today and what I want to show you at the moment. So the vision actually is that, at least my vision is that we will have a solar cells or panels that everyone can use easily at very low cost and especially in third countries like you see in this picture. And this is the goal or the vision where we are aiming for. What we have to understand today that the current technology, let's say the main technology in the solar energy in the solar cells is the silicon-based solar cells, and they are more or less reaching their limits. Okay, they are today reaching around 27% for a single crystalline silicon solar cells. This is the really high efficient but very expensive one, and this is really close to the theoretical limit. So we are there already. And still, we don't have enough renewable energy used outside. Therefore, we have to find a solution for that because it seems that this is not happening in terms of if you are keeping using the silicon. And what happened actually less than 10 years ago, and I'm talking about 2012, and this is what Mara tried to pronounce, we found a new material which called Perovskite. You see here in red, and I will explain a little bit more, of course, during the lecture, but to give you the bottom line is that in 8 years, the performance of solar cells, which are based on Perovskite material, are reaching the same like we get in a silicon, which took the silicon to get in 30 years. This is nice, but what is more nice, that the cost of those solar cells are really third of the price of what we are getting by silicon cells. And this is really something that we think will change the thinking of how to use the solar energy. Here, for example, in this graph, you can see this is the efficiency, this is a year scale. And if you look on silicon, this one, for example, it's really reaching the limit that it can achieve, while the red one is the Perovskite, and the Perovskite, at least today, theoretically, we can expect to get much higher performance with the years where the silicon is not there. So this is one point that's very important to understand, that already today we are in the same efficiency, but the cost is already much lower. And this is another example while people think that the silicon is getting cheaper, but it's not really correct, because finally today is not just we are limiting in terms of the technology, we also do not know what to do in terms of the price, and this is what we need to solve. In addition to that, of course, the population is really really wants to get more and more energy. And you see here the prediction in 2050, for example, how much energy in gigawatt we will have to consume in the world. And at the moment, what we are getting from the coal mainly is not enough. So we'll have to use the solar energy. And as much as we will make it more efficient and more cheap, it will be more available, and it will be the solution, of course. If not, so it will be much harder to get those source of energies. This is the projection of the photovoltaic cells, so what they can give us in terms of gigawatt. This is a gigawatt, the energies that they can supply, and we are today around here, 2021. We expect that this is really growing exponentially very, very fast. So which means that if we're keeping developing the photovoltaic technology, it will keep up and even more than what the world will need in terms of energy. So what next? So the next is to think how we make a solar cell that will be available for everyone. And this is what I told you, will be cheap enough and of course efficient. And this is what we are looking for. And this is actually, it's my main research area, but also it's already not just in the research. We are also going to some application. As we said before, we also establish a new company that really concentrate on how to do that. So the solution here that we found is called Perovskite. So Perovskite is a name of material. Okay, technically it's a mineral, let's say the basic Perovskite, but here it's not exactly a mineral, it's a different composition. And here it's a little bit chemistry. If you have any question, I will be happy to answer, but this is the structure of the Perovskite, which means that those balls of purple are could be those kind of atoms, could be iodide, bromide, or chloride. In each of this structure, this is an octahedral. Yeah, sorry. In each of this structure, we have in the middle a metal ion, usually lead or tin. And once this structure is formed on the surface, we have a cage that we can put our organic cation, which means this is a hybrid material composed of organic and inorganic. And I will show in a minute its properties, why it's so attractive. But you can play here very nicely with the chemistry, which means that you can change the atoms as I wrote here, you can change the organic molecule, and this will change your properties of the material. Okay, and this is something that we didn't had before, especially in the silicon material. So what is the advantage of Perovskite in photovoltaic, in solar cells? First, and I think one of the important ones, we can make it from solution, which means that today you can even print it, and this is what we are doing. You can make an ink of this solution Perovskite, and you can print it on the surface, which opens the possibility to a variety of application, to make it much more cheaper, and to roll-to-roll a process. It composed of abundant and chiplet component, as I said before. You can tune the optical properties, and you can see here in this graph, for example, this is an absorbance graph. This is the energy. The wavelength is the energy, the x-axis, and you can really push the way your material will absorb. You can absorb more or less, of course. If you want more efficient, you will absorb more. If you want, for example, I will show you a specific colors or some transparency, you can absorb less, so you can play with it quite easily. It absorbs light very efficient. What does it mean? It means that you don't need a very thick layer of perovskite. It could be very, very thin, and I'm talking about hundreds of nanometer. Nanometer, it's 10 power to -9 meter, a very, very thin film. And this is enough, which means that you don't need a lot of materials, finally, to get a nice solar cell working. And you have the bifascial configuration, and I will show you what I mean by bifascial. Finally, you can use the sun from both sides of the cell. You don't need to use just one side. You can use both, and this is really a nice and important property. So why perovskite will make the change? As I told you, it's actually going to a very efficient one, and especially it can work very efficient in low light intensity. Why it's good? What does it mean? It means that you can even use a solar cell in the room, for example. You can use a solar cell in a cloudy day, okay? Not necessarily just when you have a full sun, and it can work very efficiently. For example, today, the solar cell technologies, if you have a cloudy day, are working very, very poor. And this is this is because of the properties of the materials, and the perovskite is not in this category. It can make, as I told you, from solutions, you can make an ink out of it. And finally, you can print it also. You can tune the optical properties, and by that, you can adjust it to a specific applications. So finally, it has a very good properties that put it in a good position to be the next generation of solar cells. Potential applications that we have, for example, this you cannot do with current technologies. We can do what we are calling a BIPV, which is built-in integrated photovoltaic. So you can make a windows of those solar panels, which will be transparent and of course in colors at the same time and produce energy. You can use it for greenhouses, for example. You can use it on cars, which means that you can make it flexible, okay, as you can see here. And there are also some products already today that you can charge your phone, use your headphones, and as I told you, use it inside your home from your electricity, from your current light at home. This is very attractive applications, which were not possible before. Before, we just can put the silicon outside in the desert, produce energy, and that's all. So if we look a little bit on the perovskite from the academic point of view, as I told you, it was a really big hype from 2012. And really, my group was one of the first working on this magic material, but in a few years, a lot of groups jump in. And this is a good thing technically in a research, because then you can you put a lot of efforts to discover, to make a research on a material, and then instead of taking it 50 years, you can really squeeze it to much less number of years to get all the data and all the idea how to use it very efficiently. So how we make the perovskite, and I did here a cartoon just to give you the impression how easy it is. So usually we have two precursors. We have one precursor, it's the lead iodide or lead bromide, which means it's the D-metal ion with the halide. And this is the one precursor, and we drop it on the surface. Then we are making a very thin film out of it. This is a spin coater. This is an equipment that is rounding very, very fast and make a very thin and nice film of few hundred nanometer. And then we take this electrode and dip it in the other precursor. Once it dipped in the other precursor, you have a reaction and you get the perovskite done. So this can be done in a few minutes, and this is how it looks before the electrodes and after that. This is a brown perovskite, which means that it absorbed the whole range of wavelengths of light quite easily. But as I showed before, you can tune the properties, and you'll see in a minute. This is a picture from my lab. Some of the process we are making in this nice Glovebox. What is it? It's a box that inside you have an inert atmosphere, which means that you have usually nitrogen that do not react with the outside, which means that you can do the process without any outside conditions. It's important for experiments because then if something happened, you know it's not coming from the outside condition, it's just because you can control the condition inside. This is just for the studying of the material. Usually you have those gloves, so you go with the hands inside it and you work inside the box. Okay, so how a Solra cell looks like based on perovskite, just to makes it easy to understand and how easy actually, and this is the development we did, one of the developments. So usually we start with a glass. So it's not a silicon, we take a glass. This glass has a conductive coating. This conductive coating is like you have in your phones, in your smartphones, which is transparent. On this one, we are putting usually a nanoparticle of a material called titanium oxide. This is a transparent particles. Usually you have them, let's say you wore them in your tooth paste. Not anymore today, but they were there. And on that, we put the perovskite. This is the brown stuff here, and we put the metal contact. So finally, we illuminate from the glass side, and this is the, let's say, the most simple Solra cell of perovskite. I will show you more complicated one. So the light is illuminated from here. It's going through the glass, through the titanium particles, hitting the perovskite. And then when it hits the perovskite, what happened? It separates charges, which means, as I told you before, the negative and the positive, electron and holes. And once they are separate, one of them, the negative goes to the titanium oxide, the white here, and the positive goes to the gold contact, because from the energetic point of view, they prefer to go to different directions. And this is with this we create because we actually design it like this, okay? So once they are here and here, the negative are actually in the glass and the positive are in the metal contact, you have charge separation and you have electricity. That's all. So it's quite easy to generate out of it. You just need the perovskite to be very efficient and to put the right materials below and above it. So this is the idea. This is a nice picture of electron microscopy, which we take the Solra cell and cut it to two, and we look on the side of the Solra cell, and you can see nicely the layers. As I told you, this is the conductive coating on the glass. This is the glass. This is the titanium oxide nanoparticles, and this is the perovskite. But finally, you see here, this is the scale. This is 1 micron, which means all this thickness is, let's say, 1.5 micron, not more. So it's really a very thin coat on glass, and this generates a very efficient electricity from the sun. A typical Solra cell, as you can see here, we are doing in the lab, generate like 18 to 19%, which means that this is really comparable to what we have with silicon today. Just to give you a perspective, a Solra cell, the limit, the theoretical limit I showed you before is around 30%. So we are quite close, and this is a very good results, but it's not 100, it's 30%, and this is something important to understand. So what we can do with it, you can see nicely here how we can tune optical properties with the perovskite. As I told you before, you can change the iodide to bromide, those atoms, the purple bullets here, and as a result of that, you can tune the absorbance, you can tune the color, finally, of the perovskite. So you can tune it to a specific application, or you can tune it to how much light you want it to absorb or not to absorb. Another way to do it is to change the organic cation. You can put a smaller one or a bigger one inside this cage that still needs to fit to this cage. And this can also tune the optical properties and how much light it will absorb. So those are really quite easy techniques by simple chemistry, changing the properties. And this cannot be done in other materials. So this was the main revolution. So what else we can do with the perovskite? This is one of our recent development. And I will try to explain it nicely and easily here. So this is the perovskite that I showed you before. A nice three-dimensional material. The yellow balls here are organic cations. And we thought, what will happen if we put a larger organic cation that will not fit into this cage? Okay, what will happen? So we call it a barrier molecule, a molecule which is bigger than this cage. And if we put it rightly in the stoichiometric ratio in your flask of reaction, you can start to get a two-dimensional material, actually a layered material, which separate by those organic cations. And if we put the right amount of small organic cation and large one, you can really control the number of layers that you are getting. So this is a nice structure, you can say. Why it's good? First, one of the objectives was to enhance the stability of the material. Finally, if we want to go with this solar material to real application, we need to enhance stability. And by introducing those organic molecules, their material become more hydrophobic, which means that it become more resistive to water, to humidities that we have in the air. And this is what we did here. In addition to that, a very interesting stuff that we discover that you can tune the optical properties, which means that the number of layers here are also tuning the color of the perovskite. If before we just change the halide, this atom, iodide or bromide, here we can tune optical properties by the number of layers. So this is really nice. And the motivation here finally is to get a really small number of layers as much as possible and to get a solar cell working. Because if it's a small number of layers, you will have a lot of organic cation, which make it much more resistive to water. Okay, but on the other hand, if it's really small number of layers, the conductivity is really poor. So you have to find the balance where you have enough layers but still some resistivity to humidity. Okay, and this is the idea. This is what we want to achieve. So we tried a different barrier molecule to find an optimum how we can solve this issue. You can see nicely it's become like a platelet material, really nice because of those barrier molecules. This is an optical microscope which demonstrates this. One of the nice stuff that you can get out of it is that you can get solar cells with a very high voltage. Okay, so this is something that we thought about, but it became out that those barrier molecules produce a very high voltage. What I mean high, I mean that you can get from a single cell like close to 1.5 volt. This is close to a battery. For example, the silicon are getting half of it, okay, the maximum theoretical one. And this is really opened the opportunity to even more applications like high voltage applications. Okay, but the main problem still that we still have to face is how we can organize those two-dimensional perovskite. What does it mean? Let me go back here to the layers structure. If this structure is standing like this, then the conductivity is very poor because you have those barrier molecules which are not transport electron, not transport conductivity. Then you have to change this structure to be parallel to the surface, and then the conductivity will be much better. The question is how you organize those layers on the surface, and this is really a challenge. And one way that we thought to do it, you can see here, if so far we have an organic cation that facing, you have two organic cation between two layers, okay? We thought what will happen if we take an organic cation that have two functional groups that can close the pack, which means that we don't need two organic cation between those two layers. We need just one to close, to hold the inorganic sheets. And apparently it really helps. We get a very nice performance out of it. And the main issue is that we get a very nice organization between the electrons. So you can see this is usually what happened. And this is what happened to us if you take a nice organic cation that can force the layers to stand like this. By that, we can get both high efficiency and more stable structure of this solar cell. So this is just to show you the rationale between the development in the lab and how you can really take it finally outside. So it's all coming from the molecular level. It's not just we are just trying some stuff and let's see what happens. You really need to think what will be the direction and what you want to solve. And as I told you, the stability improved, still not the best, but we can put it in a high humidity environment, like 50% humidity. And for 250 hours at the moment, we have today even better results. So this is the initial performance. It's dropping, but you can see here nicely how the three-dimensional perovskite without the organic molecule dropping much, much faster than that. Okay, so this was one important subject that I want to show you. And the second one will be actually related to our spin-off company. And this is still on the Perovskite, but the development here was a different solar cell structure. So the structure here was based on a printing. It's called a screen printing. This is to show you very schematically. Screen printing is a technique that you use actually to print on shirts, for example. So you have a mesh, you have this kind of mesh with a very, very small holes, okay, that you can design the patterns. Then you take a paste and you brush it from one side to the other, and the paste is going through this mesh. And when you move the mesh, you have a pattern on your surface. Okay, by that you can create a very thin film, a very uniform film, and those film can be made of nanoparticles. And I will show you the structure in a minute, so how it works. And this is a nice structure that we developed for it. So we use this technique. We start in with a glass, as I told you before, also here. On that, you have the conductive transparent coating. This is the FTO, still nothing new. Then we start to print. We print a TiO2 layer composed of nanoparticles. On that, we print another layers of zirconium oxide, also composed of nanoparticles. And on that, we print a contact layer. This is called ITO, indium tin oxide of nanoparticles. All layers are transparent and all layers are nanoparticles, which means that the innovative point here is that now we come with the perovskite and we drop it and it penetrates through the all layers until the bottom. So quite easily, you print 3 layers, you come with the perovskite, it's penetrate, and it's ready, okay? And since those materials are based on oxide, are based on oxygens, they are very, very stable, which means that it's opened the possibility to a very stable solar cell. Okay, this is a cross-section, for example, you see here nicely the layers. This is finally the ITO layer. This is the zirconium oxide layer, the titanium oxide, but this is like we cut the device from this side. We wanted to check if the perovskite is really penetrate the whole way, and we have some microscopic technique to do that. And we see here nicely, this is the element analyzes how it's going through the whole device. Finally, the perovskite need to suck inside those mesopores in order to the solar cell to work efficiently. And you see here two things. First, we are getting a very nice performance today out of it with those devices, and the stability is really great. You see here for around 40, 50 days, you have very nice stability, and this is how we want it to be operate. Another interesting feature of those technology is that you can recycle it. And this is important today. What does it mean recycle? If your perovskite is degraded, or let's say you need to replace it after several years of the solar cell, of the operation of the solar cell, you just take the solar cell, you wash the perovskite. All the other layers that I print before are there, and then you introduce a new perovskite. Okay, and you see here nicely, this was the first performance. After washing and introduce a new one, it's still the same, which means, and even a second cycle, it's still the same. So you can really recycle. You don't need to destroy the whole solar cell in order to make this to happen. So this is a very nice feature that you cannot do in other solar cells. Since the scaffold of this solar cell is transparent, you can also make it in colors, as I told you. So you can make perovskite in different color, and you can introduce it into the solar cell quite easily. And I think the last interesting feature of this technology is that the company is working on is the bifascial opportunity. What is a bifascial? You see here a nice cartoon. If you put a solar cell outside in the sun, so of course the sun is hitting the solar cell from one direction, but what happened to the sun that really hits the earth, for example, or hit in other directions that then the light is coming from a different location. So you have today technologies, for example, that tune the solar cell according to the sun based on the hour of the day. But the most efficient one will be to make a bifascial configuration, a configuration that can absorb light from both sides of the cell. So you don't need to move the solar cell at all. And today the technologies, in order to do that, needs a very sophisticated layers and a very expensive design. In this solar cell, since the glass is transparent and the ITO, I told you, the contact that we print is also transparent, it can work technically in this bifascial configuration, and this is what we are getting today. So which means it's really easy. You don't need to do nothing. You just need to use the solar cell as is, and it can absorb light from both directions. And this is an inherent feature of the solar cell, which you cannot find in other technologies. Last topic I want to say, I have more time, Mara, or?
I think so, but then I would like to leave a bit for question and answers.
Okay, it's like 5 minutes and then I will be open.
Perfect.
For question. So just to show you an interesting feature that we're also doing with those solar cell, and this is in collaboration with Professor Shlomo Magdassi from my institute in the Hebrew University. It's a windows of solar cells, which means a semi-transparent solar cells. And here you see a picture, for example, of our campus, and you see through the solar cell, the campus. This is in Givat Ram campus. So what is the idea? The idea is that we can make a solar cell that will be transparent, and we can control the transparency of the solar cell. And of course, if you make a more transparent cell, you will have less efficient, but on the other side, you have more light. So if you put it on the window, so you will have the option actually to get more energy out of your solar cell, or to get more light into your room. And this depends, of course, on the building, on the design and everything. And this is something that was not possible before. And how we do it, and this is a nice technology making by inkjet printing. And how we make the transparency of the film, we print in a polymer that is transparent, and it's like balls on the surface. And on that, we print the perovskite. So the perovskite going to the sides. And finally, what stays, it's a transparent polymer. And in between, you have perovskite. So those dots of polymer gives you the transparency. If I will have more dots, it will be more transparent. If I have less, it will be less transparent. And here you see, this is electron microscope of the dots, which are printed. And here you see a transparent Solra cell, for example, of this is around 25% transparency. You can see here nicely how it looks. This is 25%, so you can see through it. Of course, you can make it more transparent, but this one, for example, it's transparent enough, and it can generate like 11% efficiency, and this is really enough, for example, to give you some light in your office, for example. And this is some technology we are going today for built-in integrated photovoltaic cells. This is a nice illustration to show you a graph that shows you the efficiency of the Solra cell and the transparency. So of course, if we are in less transparency, we can get more efficiency. Okay, but if we want more transparency, the efficiency will drop. This is theoretically what happened. I mean, we cannot find this thing, but we can try to improve it. And today we are around here. As I told you, 11% efficiency with 25% transparency. And this is quite good in terms of the industry, what they require at this stage. This is my end. This is the acknowledgement. This is actually my research group who work on those projects. And of course, finally, I am sitting, we're discussing, but they're doing the work in the lab. So for sure, all the thanks is to them, to the hard work. Without them, it couldn't happen. And thank you for your attention, and I will be happy if you have some questions. Thank you very much.
Thank you a lot, Professor Etgar. It was really fascinating. Your research is really making a better world in all senses. And thank you for this. So we are now open to questions. I can see in the chat already one question, then we can go on. Okay, Dita Broniczki, if you could write or open your microphone and ask the question.
Yeah, I see she wrote something here.
Yeah.
Hi, this is Yuda Broniczki. I would ask Professor Egar to address the problem of stability, degradation with time, and also resistance to the weather, if you have to encapsulate it, as the song you say, or not. Thank you.
Okay, thank you. Yeah, a very good question. Of course, one of the main limitation in the technology is that you need it to be stable, finally. So finally, unfortunately, in nature, we can find a good material, but it will have some disadvantage. So one of the point here is the degradation. And as I showed a little bit, the main mechanism for the degradation coming from the humidity in the air. Okay, no, I'm not talking even on rainy day. Okay, so we have to find a way, and this is what we developed in the two-dimensional perovskite, a way to get a more humidity resistivity of this material. In addition to that, and this is what you said, we are doing encapsulation to the cell. The Solra cell will be with encapsulation. It cannot survive without any technology today, you have it. But in addition to that, you also need to design your material that will be more resistive to humidity, of course. So this is coming together. And this encapsulation will also protect it from other weather influences and those kind of things.
Thank you.
Okay, please, if you have any other questions. Okay, so if there aren't any more questions, In the meanwhile, I would like to bring you the apologies of Lioz Etgar that he couldn't connect, and he was really sorry for that. And I would like to thank you, Professor Etgar, who just arrived in the United States. He had a very long flight, but still he had the strength to connect with us and give us this very, very interesting lecture. Thank you a lot for this. And thank you to all of you that participated with us. Chag Sameach, Hanukkah Sameach for those who are having Hanukkah. And I hope our next webinar. Thank you a lot to everybody.
תודה רבה. Thank you very much.
תודה.